Today, we are very happy to have Isaac Kim from University of Sydney, and he's going to tell us about moves in the radiation, robust encodings of the black hole in field. Over to you, Isaac.
All right, thanks a lot. So thanks for the invitation. Thanks for coming. So I wanted to tell you about this recent work by Eugene Tang and John Preskill. So you probably all know John Preskill. Eugene Tang is a grad student at Caltech, and he'll be moving to MIT this year. So I'll send you the slides like after the talk. So just to be clear, this presentation is based on this archive preprint and appeared in JHAB. And all of us given some versions of these talks. Most of them are very similar to each other, so you can watch them. They'll be quite similar. But there are two exceptions. So John gave 2 talks at KITP, which are related to this. And he focused more on the technical details. So if you're interested in that, I recommend you watch those talks as well. And I want to make this talk somewhat interactive. So if you have any questions in the middle, please don't hesitate to ask me. I'll be happy to expand upon the details. So let's start. As you all know, there is a famous black hole information paradox. At least semi-classically, black holes emit a black body radiation with a temperature which is inversely proportional to the mass of the black hole. And the important point is that the content of the radiation is independent of its initial state. So if you form a black hole starting from some pure state and then wait it until it evaporates completely, then it looks like the final content of the black hole is independent of its initial state. So is information about the initial state lost or not? And this is really the crux of the black hole information paradox. To resolve this paradox, several people in the 1980s and early 1990s proposed that the inside and the outside of the black hole are perhaps not separate systems, in a sense that the Hilbert space that describes the interior and the exterior cannot really be in a tensor product structure. And this radical proposal, despite its radical nature, actually holds up to some pretty non-trivial tests, such as the Hayden-Preskill thought experiment, among many other things. So, and of course, as you all know, since then, ADS-CFT came out, and the black hole complementary picture, I would say, was well accepted until in 2012.
Sorry, Isaac, could you give us a minute on the Hayden-Preskill thought experiment, please?
Okay, so it's not directly relevant to this paper, but the way I would like to
do it at the end if you think that's better. Yeah. Okay.
Yeah. But I can very briefly mention the point that the reason why I mentioned this was because they consider a thought experiment in which you throw in a quantum information into an old black hole. And their point was that this information comes out pretty much right away. So you can imagine a thought experiment in which you throw in an information and grab it from the radiation and then jump in, hopefully in a hope that maybe you can find some violation of the known laws of physics. And it turns out that you don't, but the way in which you can't do this so there is no violation, but very barely. So if you can do it only slightly better, then you may find some inconsistency in the black hole complementarity. But at the end of the day, they don't find any inconsistency.
So just to say again, so if you wait long enough outside so that you can recover the information of something that fell in, you cannot also go and meet that thing. Is that you cannot jump in and then meet that thing that fell in?
Let's see. Well, the potential tension is this. So if you consider an old black hole, and if you throw in an information, the information comes out almost instantaneously.
Yes.
So the point is, you may hope that you can just grab that information and jump to the black hole and see the copy of that information. Yes. Therefore, but it ends up happening that this doesn't. You don't see a copy of this.
And you don't see because causality prevents it. That you can't meet the thing that you I've already
That's right. That's right. That's right. You can't meet the thing that you're trying to say.
Yeah.
That's
Thank
right.
you.
So this passed some pretty non-trivial tests. Until 2012, a group of authors called EMS, Elmeri, Morrow, Potinsky, and Sully proposed what is currently known as the firewall paradox. So let me try. There are various versions of the firewall paradox, but let me try to give the original version according to my understanding. So consider a near horizon mode, let's say B, and its partner mode B tilde, which is an infalling mode. The effective field theory tells us that any near horizon mode must be entangled with its infalling partner. This is based on Hawking's calculation. But at the same time, from the perspective of someone who is looking at the black hole from far away, after more than the half of the initial black hole entropy is radiated away, B must be entangled with the early radiation. This is a very generic statement about many-body quantum systems that are chaotic. So this in itself is not a violation because it has, so the fact that B may be both entangled with B tilde and the radiation at the same time in itself is not a violation because it doesn't really specify whether there's a thought experiment in which there's an observer who can see the violation of the monogamy of entanglement. The point of the EMS paradox was that you can conceive a single observer which interacts with the radiation and perhaps extract whatever is entangled with B, and then capture B and B tilde on its way into the black hole. And then in his own local laboratory, you have 3 subsystems, B, which and something that he extracted from the radiation, and also B tilde. So it looks like he can get 3 qubits, which violates the monogamy of entanglement. And that's a potential problem. At least in the context of the thermal ADS-CFT, like in the thermal field double state, we can understand how this works in practice. In this picture, indeed, B is entangled with B tilde, and it is also at the same time entangled with the quote-unquote radiation, which in this context is really the left-hand side of the thermal field double state. In this picture, there's no violation because as you can see in this diagram, B tilde can be really thought as something that has evolved from B tilde prime, which is merely part of the radiation. So B tilde and radiation are not independent degrees of freedom. So even though B is entangled with both B tilde and quote unquote radiation, there's no really violation. Of course, this argument only applies to the thermal field double state, and the case for the evaporating black hole, there is still a paradox. And to more sharply formulate this paradox, it is helpful to note that the proper time between the event in which the infaller finishes collecting the radiation and the event in which the infaller crosses the event horizon can't be really larger than something that grows polynomially with the black hole entropy. So the point is, this is not something that scales exponentially with the black hole entropy. And the real question is, within this time, can you actually extract something that is entangled with B from the radiation? And many people argue that for all practical purposes, this will be impossible because they claimed that the computational cost of actually carrying out that experiment will scale exponentially with the size of the remaining black hole. So people had some argument that there will be some lower bound on the time it takes to actually carry out this experiment. So if that is really true, then the EMS argument in its original form will become moot.
Sorry. Just to get the logic clear, you said there was no contradiction if the radiation inside, the partner mode inside and the radiation outside was part of the same Hilbert space.
Mm-hmm.
So that's one sort of resolution. Now, I don't understand the connection of what you're saying about the computational time, how that connects with what you said earlier.
Yeah, good. Yeah, so I think I skipped one part. Good question. So I think the part that I skipped was that some people argue that the interior of the black hole is encoded in the radiation, and that's gonna that's what we're gonna critically analyze in this talk. So I'll first accept that point of view, and think about the ways in which it could go wrong. So the point is, then you might think that there is this wild non-locality between the interior and the exterior. So you may be able to violate causality, for example. And at least the first line of argument, which was something involving extracting something from the radiation, cannot be done. That's what these authors claimed. But
I'm sorry,
I would. Yeah.
I still didn't get it. I mean, if what I understood is that if the interior mode and the external radiation were part of the same Hilbert space, then there was just no paradox to begin with. So what I still don't understand what you're resolving by.
I think in that case, the quantum mechanics paradox is gone, but then there is a potential paradox in the causality, because well, if B tilde is really in the radiation, you may be able to apply some operation on B tilde non-locally. And then you can jump into the black hole and see that what you've done on the radiation affected the state of B tilde. This is the point that I want to actually emphasize more on this next slide.
Okay, thank you.
So these past authors argued that it might be computationally difficult to extract B tilde mode, even if it's in the radiation. But I think this doesn't really solve all the problem, because instead of decoding the radiation, the infaller can maybe apply a very simple perturbation on the radiation, which may perturb the interior mode. The point is, it may be difficult to extract an information, but it may be very easy to perturb the information, even though you don't know the exact way in which you are perturbing the information. And in fact, this is the argument that was pointed out by Amps plus Stanford, a follow work of the Amps paper. And they argued that even if we don't know the exact form of the interior operator, called as OB tilde, it must be some highly scrambled operator. And if that is the case, such operators generically have a order 1 commutator with any simple operator. So actually, there's a rigorous argument by Papadodimas and Raju who show that this really is the case. And this suggests that if you really want this interior operator to commute with a set of simple operators that the external observer can apply in the radiation, this is impossible, basically. At least if you want to enforce the commutation relation on the entire Hilbert space, then this cannot work. So this suggests, I think it's a wrong argument, but I'll be the devil's advocate for now. So this suggests that one may be able to alter the joint measurement statistics of the some mode B and its infalling partner mode B tilde by applying something on the radiation, some simple operation. So as an example, you can imagine beginning with some simple entangled state like 0, 0 plus 1, 1 state over B and B tilde. And by applying some simple operator, you may be able to alter the measurement statistics. So if we believe in the uniqueness of the vacuum from the infaller's perspective, this means that depending on what the infaller does on the radiation, you will get some state that is not exactly the vacuum state, so some kind of excitation. That's a rough argument. And that would be a problem because, as I said, the infaller is supposed to see the vacuum, which is unique. Therefore, at least, so if you consider two states, the state in which the infaller applies a perturbation to the radiation, and the state in which the infaller does not apply a perturbation to the radiation, at least one of the two states must contain an excitation.
Sorry, I have one more probably stupid question. Where, if we look at the mode B tilde, it's the idea is that it's encoded in some of the radiation, but I would have thought that that radiation was the radiation to the future of B tilde, sort of not in the past, whereas your infaller is coming from the past.
So I think maybe, but my perspective is that if we view this radiation plus the remaining black hole as a closed quantum system, then after the page time, let's say radiation constitutes 70% of the initial black hole entropy. Then if we believe that this time evolution of the black hole plus the radiation is unitary and chaotic, then we expect that, let's see. So the complement of the radiation is maximally mixed in that case. So therefore, whatever B is entangled with, that must be inside the radiation.
I see.
Yeah.
I see.
So, it's just an information theoretic argument.
So the inside of the black hole is encoded in the radiation late enough. I mean, everything in the inside of the black hole is encoded.
That's right. That's right. Yeah. Mm-hmm.
Okay. Thank you.
Mm-hmm. Yeah. So this is again the same point. So there appears to be a simple experiment in which you can create an excitation behind the horizon from far away and then potentially observe it, at least if you are willing to fall into the black hole. Okay, so that's really the issue. And I should emphasize that this conclusion is based on a plausible argument that there is no definition of the interior mode that is entangled with B and space-like separated from the observer at the same time. I think this is not correct, but at least at the face value, this seems like a plausible argument. So in this work, what we tried to do was to consider a extremely simple quantum mechanical model in which we can construct the interior mode, in which we can revisit these issues and construct the A definition of the interior mode that satisfies both 1 and 2 at the same time with some very small error. So it'll be a toy model of firewall, if you may. This is a bit tangential, but I just wanted to mention because this development is pretty interesting. As you all know, probably, there's a series of recent breakthroughs reproducing the page curve. All I can say at the moment is that their result shows that the fine-grained entropy of the radiation follows the page curve. And our result suggests that fine-grained entropy is practically impossible to actually measure. And from the perspective of an external observer, what you can measure in a conceivable amount of time is really the thermodynamic entropy, which is generally different from the fine-grained entropy. Just wanted to put that out there. So in our work, there are two important ideas. Both are quite general and I think kind of interesting and simple. So I decided to explain them independent of this firewall paradox and then tell you how this is related to the firewall paradox. So first is a very elementary fact on the constraint on small observers. So usually in quantum mechanics, usually we as observers are very big objects, and the thing that you are usually measuring is like a spin or electrons, some like a microscopic object. And we tend to think that given at least in principle, given a complete set of operators that acts on this Hilbert space of say a spin, we can apply any operator at our will. However, it turns out that there is a constraint if the observer is much smaller than the thing that the observer wants to measure. So more concretely, I will make a claim that let's say if we interact with n qubits, you may want to apply any operator of this form, which is a tensor product operator over like a Pauli x, y, and z. And you might think that this is always possible, but I will argue that this is not always possible, depending on the value of n. The key point is that there are two implicit assumptions that we make when we think about measurement or interacting with another quantum system, which normally doesn't make much of a difference, but in this particular case, it does. One is that the joint evolution of the observer plus the rest of the universe is unitary. In particular, if you view the observer and the object that you're trying to observe as like a closed system, then we should really assume that the joint time evolution of the two is a unitary process. And secondly, observer, even though we are macroscopic, we still consist of a bounded number of qubits. And both these assumptions will play a non-trivial role. So let's consider a simple setup, like a more familiar setup. So here we have two things. One is Alice, who is the observer, and Bob is a small quantum system. In this case, obviously, you can apply Alice can any operator that she wishes if she has good enough experimental control on Bob. And indeed, there are these quantum computing companies that allows you to do that these days. The opposite limit is the limit in which we have a small Alice and we have a big Bob, and Alice still wants to apply some operation or measure something from Bob. In our setup, Alice will be an external observer, and Bob will be the radiation past the page time. If we assume that the time evolution of the joint system is a unitary process, then generally speaking, depending on the internal state of Alice, we'll end up applying a different operator, say O sub n. So what this and because of the linearity of quantum mechanics, in some sense, the number of distinct experiments that Alice can apply on Bob is bounded by the Hilbert space dimension of Alice. And the same conclusion holds even if Alice can wield a large probe. So for example, you might think that the situation that I have in mind is that an external observer can wield an extremely large experimental gadget that interacts with the radiation. But even in that case, the fact remains that the number of distinct experiments that Alice can wield on the probe and the radiation is bounded by the Hilbert space dimension of Alice.
Isaac, just to understand, the way one is applying an operator here is that one is acting with the joint unitary on both A and B, Alice and Bob, and then just decoupling Alice, let's say tracing over the Alice Hilbert space. Is that right?
That's one way to think about it. Yeah.
Okay. Thank you.
Sorry, Isaac, what is PB?
So P is a probe and B is Bob. So it doesn't really matter what P is. The point is,
I see.
There isn't much of a difference between this and that, except that I can allow Alice to wield a large probe, and the conclusion will remain the same.
So we are including probe system in Bob.
Right. Yes.
Is that I mean, what you would like? I mean, is this realistic when you want to measure? And radiation is something, probe is something else, right?
Yeah, probe is something else. I mean, physically, the situation that I was worried about was this. So you may think of the following scenario: the radiation interacts with the galactic dust, and they may decohere. In that case, you may say that the probe is these galactic dust, which can be significantly larger than the radiation. But even in that case, in some sense, even if Alice has complete control over all those dusts, the number of distinct experiments that she can perform is still bounded by her Hilbert space dimension.
Okay.
Yeah. So.
By the way, do these ideas of observer dependent measurements and these things have they appeared before? People have talked about this, and this fact that it should be bounded by Hilbert space dimension of the observer, has this been appreciated before?
I think it's hard to imagine a situation in which this is relevant, except for this particular problem. So I'm not aware of it. So when I talk to people, I think, let's say just quantum information people, I think they agree that indeed, under these assumptions, this is a valid conclusion. But let's say in a more reasonable experimental setting, I think people haven't thought about this.
I mean,
Anyway.
okay. I mean, why can't Alice build many experiments over time and then apply a lot of them? I mean,
sorry,
I don't
Alice,
even know how to think about this. So I'm just thinking about, just a very crude kind of picture where Alice builds many probes or many experiments over time and then applies all of them.
Right. So the way I think about this is that Alice will have to choose which experiment to perform, and that choice, I guess the amount of free will that she can have is limited, because like her choosing different experiment is corresponds to orthogonal states in the Hilbert space, and she doesn't if she's trying to do too many different types of experiment, she will she just won't have enough qubits to be able to choose all of them, depending on her initial state.
Okay.
Yeah. So yeah, this is a trivial example, but I just wanted to have some numbers out there. So if you have a solar mass black hole, and let's say after the page time, Alice can apply like a single qubit operator on the qubit of her choice, because she certainly has more than 256 qubits, but the normal human does not have enough qubits to apply an arbitrary operator on the radiation. Yeah. So an important point is that just because you can interact with some large quantum system does not mean that you can apply any operator on that system. So this gives rise to an information theoretic upper bound on what a limited size observer can do on the radiation. And I want to emphasize that here, whether the operation is complex or simple has nothing to do with this argument. This is simply about the cardinality of the number of experiments that you can apply. Okay. Good. So now I want to shift gears and move on to the next constraint on the observer.
One more question. Does one a priori know that the radiation system is bigger than the observer system? Why is that? Does one a priori know that radiation system must be bigger than the observer system?
Right. So sometimes this may not be true. Like for instance, if maybe you can view the dust particles to be the observer, but later, so in that case, indeed, you can apply all sorts of experiments. But so I'll just put it this way. So at the end of the day, we have a model and we have a conclusion. And yeah, let me defer answering this question to the later part of the talk, because
okay,
I think it really goes into the interpretation part.
Okay, thank you.
Okay, so I want to talk about the second limitation on the observer, and it's complexity. So it's an old story that people argued that radiation past the page time is likely to be difficult to decode. Harlow and Hayden first argued that, and then Aronson and also Susskind argued that. And we'll make a similar line of argument motivated by Hawking's calculation. But, and morally, what we argue is very similar to these past works, but there will be some new ingredients which wasn't very obvious in these prior work. So just to be concrete, let's assume that the formation and the evaporation of a black hole is a unitary process. So you begin with a pure state and apply a scrambling unitary. And after that, you have three subsystems, E, which is the early radiation, and H, which is the remaining black hole, and B is like a near horizon mode. So you can think of B as a qubit or several qubits. So according to Hawking's calculation, any low point correlation function of E is equal to that of a thermal radiation. up to potentially non-predator correction. So our interpretation of this is the following. Actually, before I get into that, let me just say that it's pretty standard in this business, but although realistic descriptiveness is unitary, must respect charge and energy conservation, I'll just ignore that. We shall just instead assume that this is a scrambling circuit with no conserved quantities. The conclusion will not change too dramatically. And also, of course, we don't know the exact structure of this unitary. All we can say at the moment is that it is likely to be an efficient quantum circuit, meaning that the number of gates that you use will at most scale polynomially with the initial entropy of the black hole. And the pseudorandomness assumption that we're going to propose is a statement that this radiation, with this really should be E and B, is computationally indistinguishable from the maximally mixed state. The important thing is that this is computationally indistinguishable, not information theoretically indistinguishable. So,
sorry, perhaps I missed. Is the radiation and the remaining black hole is the inside of the black hole, please?
That's the inside of the black hole.
So I thought the radiation and the inside of the black hole was somehow the same space. So why are they?
Right. So yeah. So let's see. I think this is a Hilbert space from the point of view of an observer who is far away. So like from someone who's far away, you have the black hole and the early radiation so you only have the radiation and the black hole, and this is so at the end of the day, the interior of the black hole will not be encoded in H. It'll be encoded in E and H. But the H is whatever stuff that has this that is gravitationally interacting with the stars, the thing that you actually see. But the interior mode, they will not live exclusively in H. So in that sense, the interior lives in E.
I see. And sorry, this diagram which says fine matter, box and stuff, that's meant to represent saying that what was fine matter?
It doesn't really matter. Basically, let's say a shell of infalling matter, something that eventually forms a black hole.
Okay.
So yeah, what I'm doing is that then I'm waiting for, so the black hole is formed and then page time has passed, and that's all encapsulated in this UVH.
I see. And so, sorry, just ask the first question again. You said it, but I didn't quite get it. The upper thing is a state in a Hilbert space which has only two components, right? How many? So E and H are not independent.
So I assume that they are tensor product. They have a tensor product structure. So
there are three parts of the Hilbert space: E, H, and B.
Right. It should really be like a two, like the radiation and the remaining black hole. But I just wanted to differentiate B because it's convenient for later analysis.
I'm sorry. I'm sorry you said this and I missed it. But why is it okay to say that there is a tensor product between the inside of the black hole and the outside?
I think we're not really saying that the inside and the outside has a tensor product structure. I think we're merely saying that the global Hilbert space can be organized in such a way that so there's a perspective of a faraway observer which decomposes the global Hilbert space into this astronomical object tensor product radiation. But that does not mean that the interior and the exterior has a tensor product structure, because we're going to construct the definition of the interior mode, and that will indeed not live in H exclusively. It'll be in both E and H.
So what is H? I haven't understood what H is.
Let's see.
I mean, perhaps it's clarifying to think about the ADS-CFT example that people have discussed recently. There's some CFT dual to the black hole, which is being coupled to some radiation system, right? And in that context, the E here is like the bath or the radiation factor. And the H is like the original CFT factor, which is being coupled to the radiation. Is this, do you agree with this?
Yeah, that's a fair way to put it. Mm-hmm.
So in that context, Onkar, the H was really the exterior of the black hole after the island is formed, right?
Yes, it's like the CFT dual of that.
CFT dual, and it encodes the space-time region, which was basically outside the black hole, right? Not excluding the island.
After page time, yes.
So right. So but then fine. It's not. I shouldn't think of it as the inside of the black hole.
Right.
You shouldn't. No, not the inside.
Okay. Thank you. Yeah.
Yeah. So the pseudorandomness of some.
I'm sorry, just one more. I'm sorry for interrupting you.
No, it's okay. This is good.
Okay, and there was then in that case this near horizon, this near horizon mode, is that the near horizon modes on the outside or the inside?
Outside.
Outside. So why isn't that part of either? From Omkar's, the way Omkar's thinking, it's part of one or the other, right? It's part of either the field theory or the radiation. Why is it a separate mode?
Right. Let's see. So it is okay. So it is part of the early radiation. So like, but I have separated out because it's convenient for later analysis.
So this is not a tensor product decomposition. It's not distinct Hilbert spaces.
So I think like so E and B. So so everything in this picture, they have. We assume that they have a tensor product structure. Let me be clear on that one. And I think it's so okay. So maybe we can debate about that. But my stance is that the E and B, like these are just like these modes that are propagating like far away. So we thought it was okay to like think of them as having a tensor product structure, but it's an assumption at the moment.
I mean, could I think of it in the following way? You have E and H to begin with, and then you want to somehow model the evaporation process by bringing in some ancillary qubit and coupling it with H for some infinitesimal amount of time, and then you take that ancillary qubit and you throw it into E. So, at least that makes it clear that B can be thought of as an extra factor. And then, after sort of you distill some entanglement from H, you can throw it into E and think of that as sort of some model of black hole evaporation. Do you agree with that?
I'm not sure, actually.
Okay.
Let's see. So maybe I can tell you about what I think about this in the. Let's see.
Sorry, I don't want to hold you up. So
no.
If it's irrelevant, just please go ahead.
Yeah, I think at the moment, I think the best I can say is that this is an assumption, and we can talk later whether this is a valid assumption or not.
Okay, but could I ask, in the model of, let's say, the recent models that Onkar was referring to, the SYK coupled to a bath, in that context, what would B be, please?
Let's see. I believe E and B together will be the bath, and the B will be one of the qubits in the bath.
Okay, thank you.
Good. So what is our pseudorandomness assumption? It states that for any unitary U acting on the radiation, that will be E and B, using a polynomial number of gates in the remaining black hole. So let's say you try to decode the radiation by applying this U and then measure some simple operator O. By simple, I mean like a single qubit operator, for instance. And the assumption is that if you calculate the expectation value of that simple operator with respect to the actual radiation state and compute it that with respect to a maximally mixed state, then you can hardly distinguish them. And the error is upper bounded by something that decays exponentially in the size of the remaining black hole. For more realistic black holes, this assumption will probably need to change in the form that this is replaced by some thermal state. In any case, the important point is that the right-hand side decays faster than any polynomial in this size of the remaining black hole. So this may look like a very strong assumption, and it is indeed, but I just wanted to point out that there are efficient quantum circuits for which you can actually modulate some plausible assumptions for which you can actually show that. And of course, we don't actually know if this is going to hold in realistic black holes, but because such circuit exists, we may hope that because black holes are good at scrambling information, they might be actually good at them as well. But it's an assumption at the end of the day.
Could you say again what the assumption on U was? Like how big was?
So the number of gates that you can apply is upper bounded by polynomial.
Okay, got it. Thank you.
So there are two things. So we talked about the bound on the small observer and the bound and the pseudorandomness assumption. And these two give a non-trivial constraint on what the external observer can do before he falls into the black hole. So the small observer can perform only a limited number of experiments, and it is possible to efficiently generate so if the black hole radiation is actually a pseudorandom quantum state, then even though it may be possible to distinguish that from maximally mixed state from information theoretically, in practice, it might be very difficult. So these are the key observations that we made in this paper. So we will assume that the early Hawking radiation is pseudorandom, and from now on, explore its consequences. So here's the model. So again, you start with some a shell of infalling matter, and the black hole is formed, and you're past the page time. And then the external observer, before he falls into the black hole, interacts with the early radiation. So we have denoted that by this unitary U sub E. And O is the observer. Sorry, there are lots of things going on. O is the observer, and P is the probe that he may or may not have access to, and E is the radiation. And the key assumptions are that the size of the remaining black hole is much larger than the size of the observer. So of course, you may consider a large observer, which is much larger than the remaining black hole, but we would like to keep the size of the observer to be small because we want to keep the spirit of the firewall paradox, in which the observer does something outside and falls into the black hole without causing a significant gravitational back reaction. So even though there may be a big thing that is interacting with the radiation, we will simply say that small subsystem of that is the observer, and what remains is the probe. And E assumption, prior to applying this unitary, is pseudorandom. This is our assumption. And lastly, we assume that this U sub E has complexity polynomial in the size of the remaining black hole. Of course, again, you may consider unitaries which are more complex. In that case, we simply can't say much. And our goal at the technical level is to find a definition of B tilde, or to put it more correctly, find a set of operators acting on B tilde, which is in some sense fully entangled with B and commutes with what the observer does. And the goal is to find such a definition within this simple model. For that purpose, it is helpful to characterize a class of operators that the observer can apply. One example is what we call as the controlled unitary model. So this is a model in which, depending on the state of the observer applies a unitary operator U sub n on the probe and the radiation. So the observer has internal state n, and after you apply this unitary, you apply some unitary U sub n on the probe and the radiation.
So you're going to try to find these modes that will commute with anything the observer could possibly do. Is this right?
Up to an exponentially small error in the size of the remaining black hole.
Okay, yes, thank you.
More generally, of course, like generally, the observer may get entangled with the probe and the radiation, generally speaking. And when that happens, you can simply trace out the observer and end up with an effective dynamics on the probe and the radiation. And the general operation looks like this. Sorry,
I'm sorry to interrupt. Sorry, B was, you said, part of the external radiation in the simple model.
Right, yeah.
And so the observer cannot act directly on B. If he could just act directly on B, of course, he could completely change the entanglement structure of B with B.
Right, but in a trivial way, yeah. I mean, you can change it, but it doesn't really. I mean, yes. I mean, yes, you can change it, but it doesn't really, I don't know, address the paradox. Yeah.
I see.
So yeah, you may certainly consider that, but we did not consider that possibility.
Okay.
Good. So generally, you have these operators called Krauss operators, which are applied after tracing out O. Oops. Okay. So after you trace out O, you end up applying these operators E sub A on P and E probabilistically. So after you trace out O, like you get a diagram like this, and what we end up showing is this. So as I said, we wanted to satisfy two things. One is satisfying the correct entanglement property. So we wanted to find a set of operators acting on B tilde, which is entangled in the right way, first of all. So if you have a EPR pair, and if you apply an operator on one of the qubits, it's a simple exercise to show that that same state is equal to the same EPR pair applying an operator on the other qubit with the operator transpose. So you want that correct entanglement property. So that's the first equation. So and this is like a trivial thing. You can always do that. But the non-trivial thing is you want these like mirror operators to commute with a set of operators that the observers can apply, and that is E sub A for all A. So we really want that T tilde commutator E sub A vanishes on the given state for all E sub A up to this very small correction. And I really think that this condition that they vanish on the given state is important because Papadodimas and Raju showed that if you want to enforce that at the level of the entire Hilbert space, then this is impossible. So this is in some sense the best you can hope for. I will give you a sketch of the argument, which is somewhat high level, but if you have more questions, I'll be happy to tell you about the more details. So the first observation is the following. So imagine, okay, this is the same circuit diagram, but after that, you're tracing out some of these things. So you trace out this H and you trace out this P and E. And what remains is the observer and the B mode. And the thing is, because the radiation looks maximally mixed to a small observer with limited computational power, that was the gist of the pseudorandomness assumption, O will not be able to establish any form of correlation between B. So after you trace out everything except the observer and B mode, you have a roughly decoupled state up to an exponentially small error. So physically, what this means is that no matter how hard the observer tries, he will learn basically nothing about establish no correlation with the B mode. And I should also emphasize that information theoretically speaking, there exists some unitary that does establish a correlation between O and B because B is entangled with something within P and E. So by applying some unitary, one should be able to establish a correlation between O and B. It's just that that unitary is too complex to be to accommodate using U sub E. And then you can formally view this entangled state as an encoding map of a quantum error correcting code. And the way this works is quite simple. So you have this three-legged tensor here. What you do is you simply move out this B leg and simply call it as B tilde. And this way, instead of having a state, you have a map from this abstract Hilbert space B tilde into E and H. And there's a fundamental fact in quantum error correction, which is very useful and easy to remember because it's quite intuitive. And it says that if in this state picture, if the observer, which you should really think of as an environment that is trying to steal some information, is decoupled from the information that you are trying to protect, then you can correct that. You can sort of reverse what the environment is doing. So what we basically show is that for any quantum error correction code, if let's say you consider a channel in which you apply some error or you do nothing with some 50-50 probability. So if you can correct such an error, then there is a complete set of logical operators, which we call as the ghost logical operator, that commutes on the code subspace. And an important point here is that usually the logical operators, the commutator of the T and E sub A sandwiched by V is 0. That's the usual logical operators. But here, the commutator vanishes on all, like without even sandwiching it by V. So like just by applying, so they vanish identically on the entire code subspace, their commutator. So this is what we call as the ghost logical operators, and that is precisely what we needed. So remember,
I have a quick question. Sorry. So in your previous slide, is B tilde being encoded by this code in both E and H, or just E? I would have thought that B tilde.
It may be encoded only in E, but at the moment, our analysis only says E and H.
Okay.
We don't know. Yeah.
Okay, cool. Thank you.
Yeah. So the physical interpretation of this is that the V is the code subspace for the B tilde mode, interior mode, and E sub A are the set of operators that the observer can apply on the radiation, and T was the logical operators of this B tilde mode. So what this says is that they are, in some sense, effectively speaking, space-like separated, in a sense that T and E sub A, they cannot influence each other. So if you look at our paper, the way in which we derive the ghost logical operators is very complicated. So I just wanted to mention how these things work in a more simplified setup. So to make things concrete, so suppose you have a quantum error correcting code that can encode one logical qubit. And I will assume that we apply some error channel, let's say E, and suppose that this code can correct this error. The fact that this error is correctable implies that there is some linear map which reverses the effect of this error for all the encoded states. And these channels are physically implementable operations, which means that the distance between two quantum states does not increase under these maps. So if you have two orthogonal states, what you can show is that after applying the error, their distance is actually equal to 2. And the important point is that the maximum distance that you can have between two quantum states is 2. So two orthogonal states remain orthogonal. So as an example, if we stick in the logical 0 state and logical 1 state, and then into this thing, and expand this E in terms of the errors, which we can choose to be the unitary errors, then it turns out that there is a Hermitian operator, which is the projector onto the positive eigensubspace of this entire thing, minus the projector onto the negative eigensubspace of the same thing, which optimally distinguishes rho and rho prime. So if we plug in this expression, what we end up getting is a convex combination of terms that look like this. So this may look very complicated, but the important point is the following. So this Z bar G, that's P plus minus P minus, and these are both projectors which are orthogonal to each other. So their eigenvalue is within the range of from -1 to 1. And this guy also has an eigenvalue of ranging from -1 to 1. And this guy, these are just unitaries. So the important point is that this guy is always in the range of between +2 and -2. So you have a convex combination of something that lies within -2 to 2, which must sum to 2. So this means that this guy has to be 2 for all I. And once you use the cyclicity of the trace, you get an identity like this. And then again, the point is very similar. So this guy has an eigenvalue spectrum ranging from 1 to -1, and the same here. And these are just unitaries. So this first term must be in the range, must be between -1 to 1, and this one must be also between -1 to 1. So the only possibility is that this guy is 1 and this guy is -1. And after you do that, you get an expression like this, which implies that Z bar G and E sub I, they commute with each other on the code subspace. So this is the basic idea behind how you can construct these ghost logical operators. So just to give a summary of what we have been doing. So we've established that the environment learns nothing about the logical information based on the pseudorandomness assumption. And these, from that, we deduce the existence of the ghost logical operators. And as a last step, we move back from the code picture to the state picture. And this way, the ghost logical operators become like the mirror operators. Okay. So now I want to tell you about the implications by tuning the parameters. So the parameter that I want to tune is the size of the observer and also the computational power. So if you have a small observer but a huge computational power, then in particular, if you have an unlimited computational power, surely you can directly apply these ghost logical operators on the radiation of the probe and thereby changing the interior mode. So it looks like in order to really preserve space-time locality, you really need some kind of upper bound on the computational power of the external observer. The other limit is having a big observer with a limited computational power. The physical setup is that you have these galactic dust.
Could I ask a question about the previous slide?
Mm-hmm.
So, in these recent papers, people argued that there is this PETS map that one can write down, which which sort of creates excitations in the interior of the black hole starting from the radiation. So, does your conclusion imply that this PETS map, for example, is exponential complexity, or is that
I would believe so. And in fact, I would say people have studied the complexity of implementing PETS map. And it seems to have a dimension dependence, which seems unavoidable.
And it's in particular, that's exponential, essentially.
Yeah. So which grows exponentially with the number of qubits, for instance. Yeah. So I would believe this is complicated in practice.
I see.
Yeah.
I see. Okay. Thank you.
The other limit is the limit in which we have a big observer with a limited computational power. So for instance, you can imagine bringing in sufficiently many number of qubits and simply swapping your qubits with the qubits in the radiation. This way, whatever is encoded in the radiation will be transferred into the new qubits that you have brought in. And can you create a firewall this way? I don't know, but I'm not sure. At the same time, I'm not sure if this question is well defined, because I think the firewall paradox really should phrase in an operational way from the perspective of someone who does something outside and then fall into the black hole. The thing is, we may actually consider such a big observer that is falling into the black hole, but the gravitational back reaction will be huge. And I don't know if the version of the firewall paradox as we know it straightforwardly extends to that setup. Maybe if one can find the paradox in such a setup, that would be interesting. So I think a more sensible setup is having a small observer and calling whatever remains outside as a large probe. So in that setup, for each small observer, there's a sense in which the locality remains intact, up to an exponentially small correction in the size of the remaining black hole. In the sense that once you designate what the observer is, then there exists a definition of the interior mode that has the correct entanglement structure and commutes with a set of operators that the external observer can apply. So the moral of the story seems to be that in this black hole business, we need not only low energy, but low and low curvature, but also low rank and low complexity assumptions. So one last comment. So just as a sanity check, you might think that if you're inside the black hole, you can very easily manipulate the interior mode. So just to confirm that, we asked like, can we actually do that if we have access to ENH? And indeed, there's a simple, maybe simple is a loaded word, but there is an explicit circuit that realizes any operation on the interior mode. So this is possible. So I think that concludes the talk. The main thing that I want to emphasize is that black hole seems to be a very powerful and strange error correcting code that can protect quantum information against a very unexpected way. So usually when we think about quantum error correction, we are considering protecting quantum information such that it is protected against like very weak errors. But in this setup, we have a kind of funny situation in which we are hiding, let's say, 10% of the qubits from away. That's like, that is far away from you. And you have access to 90% of the qubits, which can be the radiation. But somehow the fact that the information is encoded in a complicated way prevents you from perturbing that information. So this is a very strange form of protection against a very weird form of error model. And I should emphasize that our definition of the interior mode is state dependent. And perhaps that is really necessary, but so we still haven't made progress on how to understand the observers in the interior can actually measure the interior mode. So that's, it'll be interesting to know how that actually works. Thank you.
Thank you very much, Isaac, for a very nice talk. Let's all thank Isaac. Any questions?
Sorry, could I follow up on this the last point you made? Mm-hmm. If I understood you right, and I lost some of the details in the middle, but if I understood you right, you were saying that you can always, under your assumptions, you can always find a set of modes in the external radiation that will commute with anything that that will behave for the external observer as if it's completely entangled with your B modes.
That's right. Yeah.
Okay. Now, we could imagine that there are a million other observers, not just your one external observer.
Right. Right. Yeah. Yeah. I had sleepless nights because of this problem. Yeah. But go ahead. Yes.
Okay. And your million observers can do much more than your one observer could do.
That's right. Yes.
And so naively, you would think that even if your observer can't do stuff that would make things go bad, the other guys could.
Right.
So it seems to me that the way you're getting around that is by saying that the definition of the interior mode depends sensitively on what these million other observers have done.
Yeah.
It sounds very strange and non-low. I just wanted to ask if that was reasonable.
Well, I agree. I agree that that is what we're proposing, and I agree that it is very strange. However, so I can only say what I couldn't achieve. So I tried to find a paradox involving these many observers, and somehow to find the paradox, it seems to me that all these maybe not all of these observers, but certainly more than one observer must fall into the black hole and see that their definition of the interior modes are inconsistent. I'm not sure. So, and I was not able to formulate a sharp paradox in that regard. So, so if you have two small observers, then this is not a problem, because you can, you can just say that's one slightly larger observer, and they may have like a consistent definition of the interior mode. And the tension only occurs when the number of observer is comparable to the size of the black hole that you're trying to dive into. But in that case, it's not clear if we're still in the setup of the firewall paradox. So I agree that this is very weird, but at the same time, I cannot find any like apparent paradoxes.
Thank you.
Could I ask the question? So could you explain a little bit? I think you explained this already, but I just missed it. Where exactly does this complexity bound come in your quantum error correction model? Yeah.
Let's see. So once
and
we
just like a second part of that question is whether this complexity version of error correction, do you think that also applies to the usual, ADS-CFT entanglement wedge reconstruction story?
Right. So yeah, two questions. So let me answer the first question. So insofar as so this is the point at which we completely forget about complexity. So we're like upper bounding the number of we're simply assuming that this is the maximum number of gates that you can apply, and then like we have this bound, and then that's it. We no longer think about the complexity anymore. One may like of course you may opt to use more gates, in which case you will get a weaker bound, but then your conclusion will be weaker. So that's where it implicitly comes in. And for the second question, I do believe I don't have anything concrete, but I do believe that this complexity picture still comes in pure ADS. Like if you consider like experiments that are like, let's say like, consider like CFT on a circle, and you consider a set of experiments that you can do that involves everywhere, but like you're only allowed for a constant amount of time. So like you have like for each qubit, you can only apply like a tensor product gate or something. And there's like a slightly more involved thing, like maybe you can you apply like a nearest neighbor gate, and then you apply like a nearest neighbor gate in like alternating fashion for like T steps or something. I believe the regions of the bulk that you can probe this way will be will depend on the depths, but so that'll be like a more like a fine-grained some kind of more fine-grained version of complexity will be needed to like see what's exactly going on. But I believe this is, yeah.
But it's essentially suggesting a stronger version of error correction, right? Because the usual
Right,
error
yeah.
correction is sort of against erasures, and you're suggesting that more strong error correction exists, but if you admit this sort of complexity bound, is that
Right,
a fair?
right. Yeah, that's right. So it's about so in these like erasure-based models, the name of the game is that you're given access to a subset of the qubits, and you want to recover the information. Here, right. You're given like a simplest version is that you're given access to all the qubits, but you have a limitation on the number of gates that you can apply. And you want to extract the logical information from that.
Right.
So it's a different model.
Right. And somehow the pseudo-randomness assumption is crucial though, right? For this error.
Yeah,
for
yeah,
this.
yeah. Mm-hmm. Yeah. That's right. Yeah. Without, we can't prove this. In fact, it would be unreasonable to think that one can prove anything like this.
Sure.
But yeah, it's an important assumption.
I see. Okay, thank you.
Any more questions?
Let me ask something very vague. Just going back to the state dependence and this, the fact that this sort of space-time seen by the infalling observer depends, the Hilbert space description of that depends very sensitively on what other people are doing very far away. This suggests that, I mean, if this is the right picture, it suggests that the Hilbert space for each observer in general relativity is a very complicated object, right? And depending, that has a lot of extremely non-local information and sort of almost acausally non-local information. Is that right? It's such a vague question. I'm sorry for asking.
Let's see, non-local. Let's see.
People doing something very far away could affect the state, and then would have to change your dictionary for what
right.
would you call?
So maybe I can. Let's see. I can only tell you what I currently think is plausible without very concrete arguments. But let's say I'm a bulk observer, and let's say I apply some unitary on the boundary. I believe there's a sense in which you're changing the Hilbert space, but without affecting the information. So, sorry, this is a bit vague, but so when I specify the quantum information in the bulk, I really need to specify two things. One is the state that the bulk observer sees, and the second is the encoding, like the encoding isometry. So I think ultimately, if you believe in holography, these Hilbert space of the bulk observers, these are all just different isometries. So in some sense, they are like highly non-locally related.
And the nature of the isometry changes sort of acausally if you do something far away.
That could be, yeah. could be. Yeah.
Sorry, I thought Isaac's argument, or okay, you should correct me, Isaac, but I thought your result was saying that for computationally bounded observers, you can't break the causal structure of your semi-classical spacetime.
That's true, but I believe what Shiraz was. Correct me if I'm wrong, but I believe the context was this this like many observer setting.
Yeah,
oh, I see.
Yeah.
Got it.
So the other observers could do lots of things.
Mm-hmm.
And then you would have to maneuver to change the definition of your internal mode so that it gets around that.
That's right. That's right. Yeah, that's right. Yeah. If at least that if you take our proposal seriously, that's what one should do, I think.
In that context, is Shiraz getting around the computational complexity bound by just having like a large number of spatial degrees of it? I mean, it's some sort of replacing complexity with a large memory or something like that.
Like Isaac's dust, right? There's lots of stuff all over the place that doesn't fall into the black hole, which has huge Hilbert space available to it, huge power to do things.
Mm-hmm,
right?
mm-hmm. Yeah, so I guess maybe the hope is that when this radiation interacts with this large thing outside, maybe the way in which the information is encoded, but the relative information like inside the interior, it doesn't change in some sense. So like maybe the encoding changes, but the experience is invariant inside. At least that's the hope.
Yeah, so it would suggest that there's some fantastic new way that general relativity should work to have a mathematical description of all this. Right? You showed that there's no contradiction, but then the theory has to show how it happens somehow.
That's right. That's right. Yeah. Yeah. Mm-hmm.
Yeah. Thank you.
Mm-hmm.
Okay, if there are no further questions, let's thank Isaac again.
Thanks.
Isaac, that was
Thank you,
absolutely
Isaac.
fantastic. It's the
thanks.
first quantum information talk I've attended that I've understood 60% of.
Okay.
Thank you so much.
Well, thanks for saying that.
Okay.
Thanks a lot, Isaac. It was a very nice talk. Just wanted to ask you, is there a good reference for this result you mentioned on the computational complexity of the PETS map? You were saying that.
Oh, yeah. I will, actually, I'll put it in chat right now. I can find it.
Oh, that'd be great. That would be great. Thank you so much.